Hey folks, I think it's time to get started. Welcome back to the Zoom. So as I said in the email, I'm not going to do the usual breakout groups thing this time. A lot of people have told me that that's not terribly helpful. So I'm going to try. I'm going to try and do like a more sort of standard kind of review session. I'll just try and do some problems from each of the sections that might be on the test. I hope you got the review sheet I sent around by email about a couple hours ago. I thought maybe I would just start. I'll just do like one problem from each section that I see on the sheet, and then after that we can talk about whatever you want. But before that, are there any like basic questions about the test? You know, the test is tomorrow or Friday, depending on which day you're coming in. And a lot of people I know are off campus or quarantining or decided to go home or whatever. If you're not going to be there in person, please let me know by email. I've already made arrangements with several people. It's not a problem, but we need to set it up. So thank you to those of you who have already let me know about that. Does anybody have any questions before we get down to it? Nope. Nope. Okay. Let's just do some examples then. So I'm not gonna do the ones on the paper exactly. I'm gonna leave those for you guys to try out on your own. But I'll do ones that are just like the ones on the paper. So we got, as far as the topics, it's episodes 11 through 17, and yeah, let's just get down to it. The first section is about product rule and the quotient rule, so let's try an example like that. Now, the ones I put on the paper are using only the product and quotient rule, not other stuff also, but maybe I'll do one. How about, let's find the derivative of f of x equals, how about x squared times ln of x divided by 3x squared plus 5x. How about that? This does fall in the category of product rule and quotient rule. In particular, in this example, it looks like, actually we're going to have to use both the product rule and the quotient rule, because up top you see a product, x squared times ln x, right? That's a product. And on the bottom, it's not a product, but overall it's a quotient because there is a top and a bottom. These can be a little confusing, but the way you want to approach this one is, overall, it is a quotient. It has something on the top and something on the bottom. So I'm going to do the quotient rule. When the product rule comes into play is at some point during the quotient rule, you have to take the derivative on the top. And so at that point, I'm going to do the product rule. But anyway, overall, this is a quotient rule. So I say, you got to remember the quotient rule, of course. It's the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. So I begin with the bottom, as is, times the derivative of the top, and at this point I gotta use the product rule. So the derivative of the top, so I'm gonna put some big parentheses here, and in there is gonna be the product rule. On the top, it is the first thing times the derivative of the second thing. The first thing is x squared times the derivative of the second thing. The second thing is ln x. The derivative of ln x is 1 over x. You gotta remember that. Plus the second thing on top is ln x times derivative of the first thing would be 2x. All right. So that's the derivative of the top. This is only part of the quotient rule. Remember, we got to finish doing the quotient rule. That was the derivative of the top. That's the bottom. Here I got the bottom times the derivative of the top. And then I go minus the top like it is, x squared ln x, times the derivative of the bottom is 6x plus 5. And this all over the bottom squared, 3x squared plus 5x squared, like so. That's how we do it. You should not try to simplify this, of course. I didn't ask you to simplify it, so don't simplify it. All right. That one's kind of a tricky one. Are there any questions about what I just did there? Anybody have any objections? happy to hear them. All right. I guess we'll try something else. So that was the product rule and quotient rule section. By the way, I am gonna record this and put this video on YouTube as soon as I can after class, so you can check that out. I mean, I hope you are taking notes as you usually would or whatever, but it'll be there for you to watch again if you want to. And click through those sweet ads. All right, let's try something else. So that was about product rule, quotient rule. The next section is about the chain rule. So let's see if we can do some chain rule business. So the chain rule comes up in different contexts very often. We have to use it all the time when we're doing exponential and log functions. But we use the chain rule also for sort of simple. Here's a simple kind of chain rule here. What if I had derivative of x to the 5 plus 3x squared to the 4. This is the sort of classical, easiest type of chain rule problem. All chain rule problems involve taking the derivative of the outer thing with the same thing on the inside and then multiplying times the derivative of the inner thing. In this case, the outer thing is the 4th power. So I'm going to do the derivative of the 4th power. That makes the 4 come down front and then change into a 3 with the same thing on the inside. That's how you begin the chain rule. So this right here, this right here is the derivative of the outside, the same inside, right? That's the first part of the chain rule. And then you go times the derivative of the inside. This way of thinking about it, I think, is preferable to trying to memorize the chain rule formula. The chain rule formula as written down on the page is not terribly helpful in my opinion. You just have to remember it's the derivative of the outside with the same thing on the inside times the derivative of the inside. What would that be in this case? It's 5x to the 4 plus 6x, like that. This is the derivative of the inside. That's how we do the chain rule, right? This comes up all the time when we're doing exponential and logarithmic functions, but maybe we'll just leave that till then. This is a sort of ordinary, simple example using the chain rule. Any thoughts about that one? Questions? No? All right, let's continue. Those are the easy ones, in my opinion. How about, okay, the next thing on the review sheet says logs and exponentials review. So these are things not involving the derivative, but just about simple things involving logarithms and exponents. One type of problem like that involves finding logs by hand, like without using your calculator. How about, let's see if we can find the log base 5 of 125 equals what? Find the log base 5 of 125, all right? What this means, this is not hard to do once you know what it's asking, but you'll have to think carefully about what exactly does this mean. Log base 5 of 125, it means what is the exponent 5 to what power equals 125? 125, all right? So when you see this kind of logarithm posed to you, you should try to think of it in this way as an exponent, because that, to me at least, is much easier to think of. And then you just basically have to guess the answer. What is the exponent which is required to get 125 when you go 5 to some power? Well, if you're not sure, you could just write down the powers of 5 one by one. 5 to the 1 is 5. 5 to the 2 would be 5 times 5, which is 25. 5 to the 3 would be, you multiply by 5 again, that's 25 times 5, which actually is 125. So that's the answer, 5 to the 3. So 5 to the 3 is 125, and so that means the log base 5 of 125 is 3. All right? This is how you need to think it through when someone asks you to find the log of something by hand. You're thinking, what is the exponent that I need to use in order to make something equal something? And you just have to sort of remember where these things go. This 5 goes here. This 125 goes here. And the thing you're looking for is the exponent when you're finding the log of something. All right. So another one, these don't really get much more complicated, but how about what is the log base 2 of the square root of 2. This means, again, 2 to what power equals the square root of 2. Now this one's a little weird because it's a square root of 2. If you just write down what are all the powers of 2, kind of like I did here, I just started writing down powers of 5. In this case, if you write down powers of 2, you're going to say, 2 and then 4 and then 8 and then 16. But you're not going to see square root of 2 in that list. You just have to guess sort of by other means. Do you know anything about the square root of 2? Can the square root of 2 be expressed as some power of 2? I think it can. We do this all the time in this class. The square root is the same as the 1/2 power. So 2 to the 1/2 power is the square root of 2. And so that means that's the answer to this logarithm. So log base 2 of the square root of 2 is 1/2. Because 1/2 is the exponent required to make 2 to some power equals square root of 2. All right, this is how you want to think it through for logarithms by hand. Any questions about those? Doing the logs by hand or in your head, really it comes down to guessing the exponent. And obviously I'm not going to give you one that's really crazy. If these numbers are chosen at random, you probably can't do it by hand. You'd have to use a calculator. All right, how about the other topic from that section that you should be ready to engage with is solving an equation for x when the variable is inside the exponent. So let's try one like that. How about I'll try like an easy one, and then we can do a hard one later. 4 times 10 to the x equals 28 to the x. Let's try that. Solve for x here. That's not what I meant. I meant 28, not 28 to the x. Actually, that one, as written, requires an extra trick that we never really talked about. It's not so hard, but let's do it this way. 4 times 10 to the x equals 28. How are we going to solve for this? What you should be looking to do in a problem like this is take the log on both sides, the natural log on both sides, which allows you to move the variable out of the exponent and into a coefficient, and then you can solve for it in the usual way. But before you do that, you should isolate the exponential part. So I'm going to try to first, before taking the log on both sides, you need to isolate the exponential part, which in this case is the 10 to the x. So I want to put 10 to the x by itself on one side, and in order to do that, we divide the 4 over to the other side. I'm dividing it because it's, in the original formula, it's multiplied, so to get it out of there, I got to divide. 28 divided by 4 is 7, I believe. So 10 to the x equals 7. And now we can do what I said before, which is take the log on both sides. I'm going to use the natural log, although you can use whatever log you want. You might as well use the natural log. And then the purpose of doing the log on both sides is it allows you to move the exponent into a coefficient. So this is the same as x times natural log 10 equals natural log 7. And now that the x is downstairs, we can easily solve for x. In this case, we just have to divide, because on the left I have x times log of 10. We divide both sides. I get ln 7 over ln 10, and that's the answer. Of course, if you wanted to, you could put this into your calculator, but on the test, I will expect you to leave it like that, because you can't use your calculator. All right. Any thoughts about that one? Questions about that? All right. There's harder versions of what I just did, but we can come back to that later if you want to do a harder one. For now, just to make sure that I get through everything, let's press onwards. So that was reviews about logs and exponentials. How about the next section, derivatives of exponentials and logs? So for this section, you need to remember some formulas. I will just write them down. They're not so complicated. First is derivative of e to the x. This is the best one, is e to the x. Derivative of something to the x, but it's not e. You have to do a to the x times ln a. And then we have the logs. Again, the natural is the easier. Natural is the one with base e. Derivative of the log, natural log of x is 1 over x, and derivative of log with some other base is 1 over x ln of a. So these are the formulas you need to remember. They're not so complicated. Let's just try some examples using these formulas. How about, here's a simple one, derivative of let's try 5 to the x minus 5x plus x to the 5 plus 5 over x minus ln of x plus log base 5 of x. How about that? I just put them all in there. This is the derivative of all of those things. Can we do it? Well, they're all just added together, so we just go down the list and take the derivative of each of those things. See if you can do them. Some of these are like the new stuff. Some of these are easier ones that you knew how to do even on the last test. What you're going to get, 5 to the power x. For this one, you just use the formula directly, this a to the x formula. All right, it's not an e, it's a 5, so you got to use this one with the a in it. And what do you get? Just plug in directly. You get 5 to the x, ln of, what? I wrote ln of a. It's ln of 5. I'm using the formula where a is 5. All right. Okay, that's what 5 to the x. What about 5 times x? That's considerably easier. Somebody tell me, what's the derivative of 5 times x? You can just shout it out. 5, yeah, thank you. Somebody shouted it out. 5 is the answer. Plus x to the 5, also, this is also an easy one. It's 5x to the 4, right? I will just have you note, there's a big difference between 5 to the x and x to the 5. I mean, as functions, they're very different functions, and their derivatives are totally different. It's because you got to do it differently when the variable's inside the exponent. How about 5 over x? How should we think about 5 over x? This one also is just something that we learned. We already knew how to do this before. You should think of this as 5x to the negative 1. And then when you take the derivative of that, you get negative 5x to the negative 2. All right? You know, I said this test I'm not going to ask you to do like old problems that we haven't done lately. I would still expect you to be able to do that, though. This is still very much relevant. I'm not going to ask you to do like limits or finding the derivative using the definition of the derivative with the limit as h goes to 0. That stuff won't be on the test, but something like that, sure. Okay, how about the next one? Ln of x. So this, we use the formula directly. Derivative of ln x is 1 over x, so this just becomes minus 1 over x. And then finally, log base 5. Again, this is just straight up this formula right here. Log base 5 of x becomes 1 over x ln 5. Right? That's the derivative of that. Any questions about those ones individually? All right, those are kind of easy ones because they don't involve chain rules. Mostly, usually the interesting problems with the logs and exponentials are ones in which you have to use the chain rule. So here's let's try one like that. How about derivative of natural log? Let's make it log base 2 of x times 3x squared plus e to the x to the 4. Let's go crazy with it. This is a hard one now. That's the kind of guy I am. Sometimes I go hard. What are we going to get here? So first of all, it is a log on the outside, like at the very sort of outset, at the top level, it is a log base 2. So I'm going to use this formula here. Derivative of log base a is all of this stuff. So at the first pass, I get 1 over, plugging into the formula where instead of x, I have all of that stuff inside the parentheses. So I got to put all that here. 3x squared plus e to the x to the 4. And then times ln of a. In this case, a is 2. The base of the log is 2. So this becomes ln of 2. All right. This is not the whole answer, but this is the first bit of it at least. I used the final formula there, the fourth formula, where instead of x I had all that stuff on the inside, and instead of the a I'm using 2. Okay? And now I got to do the chain rule. Remember these formulas on the left side? You always have to do the chain rule. If it's not just x on the inside, if you have some other stuff on the inside, you multiply times the derivative of the inside. So here I'm going to put some big parentheses here because it's going to be kind of a big thing that I get. Actually, I'm done with that formula. This is going to be a big thing because the inside, you can see here, is a product, right? So what I do here is going to be the derivative of the inside, and for that, I must use the product rule. So I'm going to go the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. So the first thing is x times the derivative of the second thing. I'm referring to this right here. Taking the derivative of that thing. Actually, for that, I need the chain rule, right? This is a sort of traditional chain rule with the exponent on the outside. So it becomes 4 on the front. Same thing on the inside to the third power. And then times the derivative of the inside is 6x plus e to the x. That's the derivative of the inside, right? 3x squared became 6x. E to the x became e to the x because the derivative of e to the x is e to the x. All right? This is not the whole thing. I'm trying to erase here. Remember, I'm doing the product rule. I need to continue the product rule. Plus, this, what I've done so far was the first part times the derivative of the second part, and now I go plus the second part like it is, 3x squared plus e to the x to the 4, times the derivative of the first part is 1. And this is the whole answer. All right. That's got a lot of ins and outs, as they say. Any questions about that? That's a hard one, in my opinion. Not too hard for the test, but it's a hard one. All right, great. Let's talk about. So we're into the last section on the sheet, which is increasing and decreasing. That's sort of our new topic for this week. We do still have homework due this week. Remember? Oh, does someone have a question?
Sorry about that. Yeah, I had a question. Sorry about that.
Yeah, sure.
For the ln2 on the bottom of that comes from the log base 2, correct?
Yes. So what I'm using the formula here, where
I see what you're doing. Yeah, okay.
that is this part, and then the ln a is right there.
Okay.
I use 2 here because the log is a base 2 here.
Okay.
Yeah. Yeah, it's a complicated one. All right, let's talk about increasing and decreasing. That's the new material for this week. Yeah, I was saying we still do have a homework assignment due this week about increasing and decreasing. These problems tend to be kind of long. I wouldn't say they're especially hard, but it'll take you a while to do even one of these problems. But here, actually, not what I'm about to say. This is a simpler thing. If I show you a picture, I might ask you about increasing and decreasing functions on a picture. Let's see if I can do this. How about that? This is a graph of a function, f of x. And let's say your job is to give me intervals where f is increasing or decreasing. All right. Intervals where this function is increasing or decreasing. If you're looking at a picture, if you know what to look for, this is not difficult. Increasing means it's going up as you go to the right. That means like this, up as you go to the right. Decreasing means down as you go to the right, like that. So maybe I'll use my colors. Increasing would be like here. It's going up as you move to the right. Also here, you just need to look on the picture and try to identify all the areas in which it's moving up as you go to the right. I think actually that's all. Those two regions are the only places where it's increasing. And the other regions, it's decreasing. So like here, it's going down, and also here is going down. And that's all I'm asking. And I said, give me intervals. So you have to, if you want to report that as intervals, I would say it's increasing on intervals. There's 2 of them, right? And when you specify intervals, you're always describing the x values. And in this case, I would say the interval from 1 to 3, that's the sort of blue blue zone over here, right? That's where it's increasing over there between x equals 1 and x equals 3. And then also over here from 5 and everything to the right of 5. And so I would say and the interval 5 to infinity. For this kind of problem, you really should always use open intervals. It's because at the number 5 specifically, it's not increasing. That doesn't count as increasing right at that point. Right at that point, it is neither increasing nor decreasing. Okay, so that's where it's increasing. Where is it decreasing? You just say the intervals of what I drew as the green regions. So it's decreasing on, I would say, minus infinity to 1. That's this one over here to the left of 1. And also in here between 3 and 5. So interval 3 to 5. All right, that's where it's increasing and decreasing. So I hope you agree with me. I said if you know what to look for, on a picture it's easy to say where it's increasing or decreasing. More interesting would be if I tell you an equation and you have to figure it out without seeing the picture. So those are the ones that will take you several minutes to do. Let's try. I'll just try one of them. I'm gonna copy this one out of the textbook actually, because these ones, if I just invent it at random, it'll probably have some messed up numbers in it. So I'm gonna try, in case you care, this is section 5.1, number, let's try number 8. Yeah, let's try number 19. I hope that this, I don't know the answer. Is that on the homework? I don't want to do one that's on the homework. Sorry. I'm looking, I'm checking. Checking the homework. No, that's not on the homework. All right, let's do it. 5.1, number 19. Hopefully the numbers will not be weird. Well, we'll see. If it is, I'll just bail and choose a different one. F of x is x to the 4 plus 4x cubed plus 4x squared plus 1. All right, let's try it. And your job in this problem, give me intervals where it's increasing or decreasing. Okay, there's a bit of a procedure that you got to go through when you do a problem like this. It begins by taking the derivative and setting the derivative equal to 0. That is to find the critical numbers. That's what we call the points where the derivative equals 0 or the points where the derivative does not exist. So let's take the derivative. I get 4x cubed plus 12x squared plus 8x. I like the look of this. This is where we begin to realize if the numbers are too weird to handle. Let's see if we can simplify this. I'm going to try to simplify as much as possible because we have to do some stuff with this derivative for the rest of the problem. So we can factor out 4 from everything, and actually we can also factor x from everything. So I'm going to factor 4x out of everything, and we get x squared plus 3x plus 2, right? And then we can continue to factor that. 4x, I believe it's going to be x plus 1 and x plus 2, isn't it? I think that's what we get. So this is, that's as simple as this is going to get. This is my formula for f prime of x. Here we go. All right. Okay, remember I said we're going to find the derivative, just did that, and simplify as much as we can, well, I did, and then see where the derivative equals 0 and also when the derivative does not exist. So I need to check when is f prime equal to 0. I set this equal to 0. This should be easy because I already simplified it as much as I can. What do we get when we try and solve this for x? Well, I have 3 things. Each of them multiplies to be 0, which means I can break it up like this. Either that one is 0, or that one is 0, or that one is 0. And then these give me 3 separate answers. X equals 0, x equals minus 1, x equals minus 2. All right, so I have 3. Remember, these are called the critical numbers. That's points when the derivative equals 0 or the derivative does not exist. The critical numbers. What about when the derivative does not exist? It doesn't matter in this problem, but I might as well say. You need to check when the denominator equals 0. That's typically is what causes a DNE kind of situation, but that's not going to happen in this case because there is no denominator. So I'm just going to put a little NA. We don't. There's not any points where the derivative fails to exist in this problem. So I just have the 3 critical numbers, and I'm going to make a little chart. I hope you remember the procedure. I'm going to make a chart involving my 3 critical numbers, and I'm going to write them in numerical order. They are -2, -1, and 0. So those are my x values. And then we're going to try to determine the signs of the derivative on this chart. So the derivative down here equals 0 at those 3 numbers, because that's the point of those numbers. They are the ones which we found when we set the derivative equal to 0. And then I need to figure out the signs in between those numbers. So we are going to choose our favorite values on the in-between regions. What I mean is like in here, in here, in here, and in here. The in-between regions, choose your favorite number in each of those and figure out what the sign of the derivative is. So let's start with, to the left of -2, I'm going to use -3 to plug in. I might as well. For some number less than -2, I choose -3. I'm plugging it into the formula in the box up here. This is why I put it in the box. We're going to be using that formula for all of these. I plug in -3 up there. I get, what do I get? 4 times -3 times -3 plus 1 times -3 plus 2. Now, I don't actually care what the number is. I just care, is it positive or negative? And when you have things multiplied together, you can think of this in terms of products of positives and negatives. Like this one is a positive, that's a negative. This is a negative, right? -3 plus 1 is -2. And then -3 plus 2 is also negative. So here I have 3 negatives. That means this answer is going to be negative, all right? If you have a positive times a negative times a negative times a negative, the answer is negative. So up on my chart, I'm going to put a big old line right there. That's a big minus sign, all right? In each of these spots is going to come a plus sign or a minus sign. Okay, that's the first one. Let's just do the rest. Now I need to choose my favorite value in between -2 and -1. Actually, I don't really like any of those values, but I guess I'll have to choose -1.5. Usually I try to choose some number which is easy to plug into the formula. -1.5 isn't great, but it'll have to do. So I'm going to go f prime of -1.5. This will be 4, again, using the formula in the box. 4 times -1.5 times -1.5 plus 1 times -1.5 plus 2. All right. What about these? Are they positive, negative, or what? 4, of course, is positive. That's a negative. -1.5 plus 1 becomes positive. -1.5 plus 2 is also positive. Sorry, that's not right. This -1.5 plus 1 is not positive. It's negative. It's -0.5, isn't it? So what do I get here? This is positive, right? I have 2 negatives. 2 wrongs make a right. And so I put a big plus in this region on the chart, because in between -2 and -1, the derivative is positive. All right, and we continue. I got to use between -1 and 0. Let's use -0.5, -0.5. So I'm going to go f prime of -0.5, plugging into the same formula in the box. Can't really see it anymore. How about that? I get 4 times -0.5 times -0.5 plus 1 times -0.5 plus 2. This is positive, negative, positive, positive. So I end up getting a negative this time because I have only one negative. So that's negative in there. And then finally the last one. Your favorite number to the right of 0, how about 1? F prime of 1 is 4 times 1 times 1 plus 1 times 1 plus 2. These are all positive, so this is positive, so this is positive here. All right. This is all the work is really done at this point. We now just need to report what's the answer. I'm trying to say intervals where the function is increasing or decreasing. Increasing means the derivative is positive, so I'm going to say it's increasing on, that would be here, the positive ones, right? Here and here. There's two intervals where it's positive, and we write them down. -2 to -1, and 0 to infinity. That's the interval on the right side. And then it's decreasing on the interval -infinity to -2. That's the interval on the left. And then -1 to 0. And that's how we do it. Takes you a while to do these problems, like I said before. Although I think each individual step is not so bad, but it'll take you some time to get to the end. And I think that's all I had as far as, going through the sheet. I just did one from every section. I didn't do the hardest ones every time. Are there particular ones that anybody would like to go back and do another one of, or do a harder one of, or maybe problems on the homework that you want some advice about? What do you say? We got about 15 minutes left.
Can you do number 29 on the latest homework we had?
Sure. From 5.2 or 5.1?
I believe it's...
Oh, sorry. They're all 5.1. Yeah.
Okay,
29.
yeah.
Okay. Yes. I'll make up one that's like that one. How about that? Let's do... Hopefully the numbers won't be crazy in this one. But we'll take it as it goes. Let's try that. I don't know how this is gonna go, but let's try it out. All right. This is one of the increasing, decreasing ones. So intervals for increasing, decreasing. All right. We need to do the same business, the same steps that we did before. So the first step is take the derivative and then simplify as much as we can. All right. I have 3x minus 5 times the natural log. So the first order of business on this problem, make sure that you don't misinterpret where the parentheses go. This is 3x is one thing, and then this is another thing, and they're being added together, or they're being subtracted in this case. So when I take the derivative of two things which are being added together or subtracted, we just do the two derivatives separately. So I begin by finding the derivative of 3x, and that is, somebody shout it out. 3, yes, thank you, shouter, whoever that was. And then, now the log part. Well, first of all, I have minus 5 in front. That's a coefficient in front of the log, and so it will remain as a coefficient in front of the answer, because when you have a coefficient and you take the derivative, it just stays as a coefficient. And then what's the derivative of ln x plus 3? It would just be 1 over x plus 3. And then I do the chain rule, multiply times the derivative of the inside. But in this case, the derivative of the inside is just 1, right? The plus 3 will go away in there when you take the derivative. So this is y prime. Any questions so far? Ordinarily, I would not try to simplify at all. I'd just leave this as my answer. But in this case, actually, there's not much you can do with this. To me, I like it better when it's like this. But it doesn't really matter. This is the derivative. All right. Okay, we got to say when... what are the critical numbers? That is, we set the derivative equal to 0 and solve, and then we also say when the derivative does not exist. So let's set the derivative equal to 0. Y prime equals 0. That means 3 minus 5 over x plus 3 equals 0. And we got to solve this for x. In this case, I would put the fraction on the other side by adding it. So it just says 3 equals 5 over x plus 3. And then I'm going to multiply the denominator over to the other side. 3x plus 3 equals 5, like so. And keep going to solve for x. You distribute the 3. 3x plus 9 equals 5. Solve for x, I would subtract the 9. I get 3x equals 5 minus 9 is negative 4, and then divide the 3. So x is negative 4/3. So this is a critical number where the derivative equals 0. And also, we need to find critical numbers. Critical numbers also exist when y prime does not exist, right? You also need to check when the derivative does not exist. You do this by looking for points which make denominators equal 0. And in this case, actually, we do have such a point. There is a denominator. What is the x value which makes that denominator equal 0? You could probably guess it's negative 3. Or if you're having a hard time guessing, you just set the denominator equal to 0. Negative 3. So these are two critical numbers, negative 4/3 and negative 3. All right. And so on my chart, I'm going to make my chart here. Do I have room over there? You might. No, I guess I'll do it over here. Make my chart here. It has labeled points negative 3 and negative 4/3. Negative 4/3, of course, is like minus 1.3 repeating, which is why I put it to the right of negative 3. These are slightly weird numbers, but I think it's going to work out okay, maybe. I don't know. We'll see. Yeah, it's probably all right. Maybe not. I might need to use a calculator for some of these steps. But on the test, I wouldn't give you one that requires a calculator, although I would choose the numbers more wisely. These, I just made the numbers up out of nowhere. Let's see if we can finish this off. These are the x values. What about the f prime values? Well, at negative 3, the derivative does not exist. And at negative 4/3, the derivative is 0. All right? Now, an interesting thing about this problem, this is a subtlety that I probably wouldn't expect you to realize on the test, so I wouldn't mind if you don't do this. But in this particular problem, you will notice that the inside of the log in the original formula here has this x plus 3. It is a fact that you can never take the log of a negative number, which means if the x is less than negative 3, actually the function as a whole does not exist at all. So the interpretation of that is like over here, you don't even need to consider those values at all. And if you look up the answer to that one on the homework, if you look up the answer in the back of the book, you will notice something slightly weird about the way they say the answer because of this fact, which is the only reason I'm telling you. It's ordinarily I wouldn't expect you to notice this, but we're not going to consider values less than 3 because those are not even part of the domain of the function. Anyway, let's try and continue or finish here. I'm going to choose two values to plug into the derivative. One should be, remember this is negative 3 here, so one value should be in this range. I'm going to choose negative 2 because that's a fairly nice number, which is in between negative 3 and negative 1.3 repeating. So I'm going to plug that in. And then I'm also going to the right of that number, I'm going to choose f prime of 0 for the other interval. Anyway, the first one, f prime of negative 2, I plug negative 2 into the original formula, or not the original formula, into the derivative. In the box right there, I plug x equal negative 2. This is 3 minus 5 over negative 2 plus 3. And I have to decide if this is positive or negative. This is one part where you might have to use a calculator if I was being unkind about choosing the numbers. So this is 3 minus 5 over 1, isn't it? Actually, this I can say, it is negative. That's 3 minus 5, which is negative 2. So this is negative. Negative. So right here, the function is negative. All right. And then I plug in 0. I think this is going to go fine with the numbers. I get 3 minus 5 over 0 plus 3. This is 3 minus 5/3. What is 5/3? That's like 1.6 repeating, isn't it? It's 1 2/3. This is positive. right? This is 3 minus 1.6 repeating, which is still positive. If you're doing this on the homework, you can use your calculator for steps like that. It's a little tricky. Anyway, positive over here. All right, and now we're basically done. I can say that f is increasing where you see positive down there. So that's on the interval minus 4/3 to infinity. And it's decreasing on the interval minus 3 to minus 4/3. And I'm just not going to say anything about that other interval because that's outside the domain of the function. All right, that's a hard one. The one in the book I think is a little easier because the numbers turn out a little nicer, but you should do it in the same way. Did you? I don't remember who asked me that, but does that sound all right? Any follow-up questions?
Yeah, that was good.
All right. Thank you. I appreciate the affirmation.